Let's now talk for a while about QuickCheck. And as I said this morning, I'm going to take a building it up from the bottom approach. So the very first thing is generating random data. And this is kind of the heart of property-based testing. We'll have quite a bit to say as we go along about how to do it, but for the moment, we're going to keep it pretty simple. So in QuickCheck, the fundamental tool for generating random data is a monad called G. Inside of Coq, it's kind of an opaque thing. It gets extracted to OCaml code that actually uses the OCaml random number generator to generate seeds, but we don't need to really care about that at the Coq level. So let's see. Yeah, so intuitively, the elements of G of A are random generators that you give it a seed, and it gives you back an A. And there are lots of primitives for building random generators. That's, in a way, what QuickCheck is all about. And one of them says, is called return gen. It says, you give me an A, and I will give you a G of A that always returns the A that you gave no matter what seed. So it's a constant random generator. So if we now use the sample command from QuickCheck, and by the way, I sometimes say QuickCheck and I sometimes say QuickChick, and they are the same thing for present purposes. In fact, I think you can even use both spellings in the way that you invoke it. But never mind that. So sample is a command added to Coq by QuickCheck. And if you sample a generator, what you get back is a list of a dozen or so elements that it generates using random seeds. Here we see that all of the elements are the same, no matter what. Sorry. More interestingly, if we have a random number generator for A's, and we have a function from A's to random generators for B's, we can plug them together to get a random generator for B's. And this is just the monadic return and bind that make G into a monad, meaning that we can use convenient monadic syntax for it. Okay. Now, here is a more interesting generator that actually does something. It's called choose. And it says, tell me a type which is an instance of the choosable from interval type class. And then we'll need a pair of elements of that type that specify the interval. And we'll get back a generator for elements of that type lying in that interval. So for instance, natural numbers are in the choosable from interval type class. And so if we choose from the interval 0 to 10, we get a generator that gives us back numbers from 0 to 10 inclusive. There's a generator called list_of that takes a generator for A's and gives you a generator for lists of A's. So if we sample from list_of choose 04, we get back a list of generated lists of natural numbers. A similar one is called vector of. So this also generates, this also constructs generators for lists, but you specify the length of those lists, and all the lists you get back have the same size. Okay, so it's clear why all of these lists are the size that they are, but how do we know what size these lists should be? And the answer is that inside of G, in addition to kind of managing the way that, that the random seed is propagated from through the monadic bind, we also maintain a maximum size. So whenever we have a G, it comes along with a maximum size for the structures that it will generate. That is to say, GA really just means nat, that is size, arrow seed, arrow A. One thing to know is that when you ask QuickCheck to search for counterexamples, it will first start with a very small size bound and then gradually increase so that you get bigger and bigger, so that smaller examples will.
Right? Of course, as we note here, because EQ can be applied to any type, it's polymorphic in the type of its arguments. So if we check the type of EQ, we'll see it takes a type, it takes two arguments of that type, and it returns a proposition, a statement about those particular arguments. Okay, here's the interactive part. I will ask you, what is the type of the following expression? Think about it, and I guess raise your hand when you're done. Okay, someone shout it out. The type of the following expression is, oh, 1, yeah, sorry. It's like, give the number, yes, thank you. Yeah, that sounds right to me. Okay, what is the type of this expression? Think about it. 2. Is it? It's, okay, so I have, who thinks it's 1? Okay, that 1 is correct. Okay, so why isn't this 2? So, yeah, this is a little bit tricky. And yeah, we'll get to that point in a second. So this is a proposition. So this is just a mathematical statement. So this for all is just one way we have of building up propositions, right? So this is, it's just a statement, so it has type prop. What is the type of this expression? 1, right. Exactly right, because again, this is just some assertion. It turns out that this is a not true assertion, because if n is 0, this won't hold, right? So this won't hold for all n. But again, we don't care about truth, we're just caring about assertions. Okay, what is the type of this expression? Think about it. 4, the statement is 4. Okay, why is this not typable? Why does this make sense? Well, think of it this way. This for all quantifier quantifies over some argument, and it's followed by a proposition, right? So, oh, okay. So the expression that follows the for all quantifier, what type does it have? Nat, right. So you can't, the for all quantifier expects to be followed by a proposition. It's followed by something of type nat. It thus doesn't type check. Coq will throw a typing error. Here we go. What is the type of this expression? Nat to nat. Yes, 3. Exactly right. Because it takes an argument of type nat and returns a natural number. What about this expression? 2, exactly right. So here is an example of an expression that takes a natural number and gives you a prop. a proposition, as opposed to that for all statement, which was itself just a proposition. Okay. Oh, here's a good one. Which of the following is not a proposition? So which of the following expressions, if you checked it in Coq, would not give you a prop back as the type? 3. Yes, exactly right. What is the type of that expression? Bool, exactly right. Yep. Okay. Okay, so again, just to recap, propositions are simply the type that are assigned to statements of mathematical facts. And again, these are first-class objects, so in Coq. So yes.
So is the type prop inductively defined? If so, what are its inputs?
No, it is not inductively defined.
Can I
So
define my own prop?
yes. And in fact, we will see how to define your own inhabitants of prop tomorrow morning. But the way to think of this right now is that just as type is sort of the uber type for many things, prop is the uber type for propositions. Okay. And just as you can introduce your own types using the inductive keyword, you can introduce your own propositions in a way that we'll see tomorrow morning. I don't want to give it away. But before we, yes?
So if I have a free variable that's not quantified, does that count as a prop? Like x plus 5 equals 7?
If you just had the expression x plus 5 equals 7. Now, assuming that x had not been defined previously, it hasn't been assigned a definition, Coq will throw an error because you're not allowed to have an open expression like that.
Okay, so I can't get a free variable in Coq like that. And assigned, it's not.
It is not a well-formed expression.
It's not well-formed.
Yes. Every variable needs to be bound by a quantifier or be attached to some definition. It's a good rule of thumb. Yeah.
So if type is the type of types and prop is the corresponding one, why do we have this distinction? Why don't we have propositions as types?
So you're asking what is the distinction between prop and type?
Why are we making this distinction?
So the reason for this, I don't want to get into too much detail, but the intuition is that props are referred to proofs, and these things aren't computationally relevant. And at a high level, what this means is when we use Coq's extraction mechanism to produce equivalent OCaml expressions, everything that lives in type will actually produce an OCaml definition, and things that live in prop will get erased. And there are other deeper reasons for this, but
So it's not just a practical erasure annotation. So if I wanted to have propositions as types, I could just interpret my types as propositions, but not as prop, and then they would be computationally relevant when we extract an algorithm.
I think the short answer to that is yes.
Make sure to repeat questions for that.
Oh, thank you. So let me see if I can repeat your question. Your question was, could we also define similar statements and assign them type and have them be computationally relevant and get extracted? Was that the question? And the answer is yes. You can do that. But indeed, part of the reason for using prop is as a signal that you don't want this to be extracted. It is not important. It is a mathematical statement, something that doesn't live, it does not represent a function or a term that you want to be computed. I think it's the right intuition. Any other questions? Other questions? Nope. Yep.
So basically, props are those objects. So we attach those to props.
So yes.
Expression of type prop. We can do a proof for that.
Yes. So the question was, do expressions of type prop? When we want to write a proof, we have an expression of type prop, and we write a proof for it to show that it's true, and that is exactly right. So when we define a theorem, we make a statement. The statement has type prop, and the proof script we write generates evidence that that assertion is true or statement is true. Yep. Okay. So if there are no more questions, now we're going to look at how to, so far, like I said on the first slide, we've only seen 3 ways of building up props. We have for all quantification, we have arrows for implication, and we had equalities. So now we're going to see how we can build up propositions, larger propositions, using a variety of logical connectives that should hopefully look familiar to you. The first of these is, of course, conjunction. So conjunction or logical AND is something that people may have seen before, probably have seen before. And this is just a way of asserting that facts, propositions A and proposition B are both true. And we write this using the logical AND connective, which looks like a little wedge. So as an example, here is, we're asserting that both 3 plus 4 equals 7 and 2 times 2 equals 4. So let me switch over to my proof buffer here. Oops. And make sure that this is readable for folks in the back. This is an example. So before, we had a couple of tactics that allowed us to solve goals of the form, x equals y. Right, we had this reflexivity tactic. And correspondingly, there's a tactic that lets us solve goals of the form, or make progress, I should say, on goals of the form A and B. And in particular, the tactic we use for logical AND is called the split tactic. So just off the top of your head, if you want to prove A and B, what do you need to prove? A and B. Right, you need to prove A, and you need to prove B. And that is precisely what the split tactic does. I mean, it follows this intuition precisely. So here we go. Oops, let me bump up the size here. Hopefully. There we go. So when we use split, we're going to get 2 subgoals. So this works on, for right now, we can just imagine this works in goals of the type A and B, and we call split, and we get 2 new subgoals, proving the left conjunct and proving the right conjunct. And of course, once we've done that, we can apply the tactic that we have in hand for dealing with goals that look like equalities. So reflexivity solves this goal, and reflexivity solves the next goal, as you might expect. Similarly, this pattern of using split works for any proposition. So if we want to prove, we can write a proof that sort of exhibits this fact, that for any A and B, if we can show A and we can show B, then we can show A and B in just the way that you would probably expect. Okay. All this slide is saying is that this AND intro lemma that we proved before has the same effect as using split. It's going to generate 2 subgoals, one for each of these assumptions of this proof of the AND intro proof. So if we apply AND intro, we're going to end up in the exact same proof state with the same subgoals that we had when we used split. Yes, I'm going to skip over the next one because we're running a little bit behind because of our AV issues. Okay, so this is how you reason about goals or manipulate goals which have a conjunct in them. What if we have some conjuncts as a set of hypotheses? What if, for instance, we know that n equals 0 and m equals 0, and we're trying to prove that n plus m equals 0? Okay, so this is how do we, whereas before we were sort of working backwards from the goal, here if we have some AND fact and we want to work forward from that, how do we do it? Well, the solution is to use the destruct tactic. So in much the same way that we could, well, I want to say that. So here we can do intros, and now H has type n equals 0 and m equals 0. And when we destruct H, what do we get? Well, we get 2 new assumptions, namely the left conjunct and the right conjunct. This as statement here works just as we saw before with the destruct. It gives names to each of the assumptions that we're introducing to the goal, or into the proof. And now, once we have these in hand, we can actually rewrite with Hn and rewrite with Hm. And now we have 0 equals 0, and we're done. So okay, so why did we have to do that? Well, imagine we tried to, oh, nope, I'm not going to go out. I'm not going to do that. Okay. Not going to go overboard. Okay.